Swayam Prabha. Digital India. Educated India.
Welcome. In this lecture, we will start our study of nonlinear optimization techniques, and in this topic we will devote 3 to 4 lectures, and in the current lecture I will first summarize the general methodology of optimization and briefly recapitulate the topic of single variable optimization, which you are already conversant with, and continue into developing the conceptual background of multivariate optimization. The actual multivariate optimization methods will be taken up in the next lesson. First, in any typical situation where you encounter an optimization problem, to begin with you will have a number of variables which you can choose in order to minimize or maximize some function. That function which you try to minimize or maximize is called the objective function, and among the variables which you can choose in order to have the minimum or maximum value of the objective function, those underlying variables are separated into two parts. One of them, that is some of the variables, you can treat as parameters which are kept constant for one particular study. In a particular problem, you may choose to keep all variables as design variables in hand and process all of them together. On the other hand, some of the variables at some situations are kept constant as parameters. After fixing the values of the parameters, the remaining variables which in a particular study you want to explore in to get the best possible value for the objective function, those only are treated as the variables of the optimization problem. And a typical statement of an optimization problem goes like this, in which you say you want to minimize a function of x subject to certain constraints. So, there may be an optimization problem in which there are no constraints, or there may be one in which there are constraints. Constraints are again of two kinds. One is inequality constraint, the other is equality constraint. Now, after formulating the problem, now this formulation part comes from the domain in which you are going to apply the optimization methods. Now, after studying the optimization methods, you would notice that in almost every branch of science and engineering and even humanities, quite often you come across situations where many problems can be solved through an optimization formulation. The problem may be one of explicit optimization, where you actually want to minimize or maximize something, or many times it happens that the actual problem is something else, but you can reformulate it in the form of an optimization problem. For example, in the last lecture we formulated an equation solving problem in the form of an optimization problem. So, there are many such problems which can be formulated in the form of an optimization problem, and then optimization methods can be used in those problems with advantage. Now, after the formulation is made from any given field, then you look for a suitable optimization method or algorithm to find a solution of this problem. Now, any point x, any variable value, any set of values for the variables x that satisfies these constraints, g x is less than or equal to 0 and h x equal to 0, the given constraints, any such point is called a feasible solution. That is, it is allowable, it is permissible by the constraints imposed on the problem definition itself. And out of those feasible solutions, you try to find the one in which the function value is minimum, if it is a minimization problem. The optimization problems can be of minimization or maximization type, but in most of the theory that we discuss, you will find that most of the time we are talking about minimization. Fixing our attention to minimization problem helps to keep the entire theory in one standard form. If a problem is of maximization, then we can always try to minimize the negative of the objective function. So, this is typically done in order to avoid the hassle in the notations itself. Now, after you apply some optimization method, a good number of them we will be studying in this course. So, after you apply that method, you get a solution which is the solution of this optimization problem. That means it minimizes the function, objective function, and satisfies all these constraints. After getting that solution in hand, quite often you want to find out whether the parameters, that is that subset of variables which you kept fixed, whether it was a nice idea, whether it was a wise idea to keep those values fixed. So, in that case, after you have got the solution in hand, then you conduct a sensitivity analysis. You try to find out that how sensitive is this solution that we have got in hand, how sensitive it is to the values of those parameters. If they are found to be very sensitive, then you try to see whether those parameters can be also changed in order to get a much better solution. On the other hand, if you find that the solution is quite insensitive to the parameters that you have fixed as parameters, then you say that fixing that is a wise idea. Unnecessarily, we need not conduct the optimization process with too many variables. Now, optimization problems, as I told you just now, can be unconstrained without these constraints, in which case the entire space of X is feasible, or they may be constrained. And in that way, we classify optimization problems, and for that matter optimization methods, into unconstrained optimization and constrained optimization. Obviously, unconstrained optimization problem is easier to solve compared to constrained ones. Then you also classify optimization problems as linear and non-linear problems. If both the objective function and the constraint functions g x and h x are all linear functions, then you call the optimization problem a linear optimization problem or linear programming problem, LP problem. On the other hand, if either the objective function or any of the constraint functions is non-linear, then it is a non-linear optimization problem or non-linear programming problem, NLP problem. Now, you could also classify the optimization problem as single variable and multivariable problems. Single variable problem has a single variable, and in multivariate problems you have several variables in hand with which to play around to minimize the objective function. Now, you will notice that when we classify optimization problems as unconstrained and constrained, and in another way we classify them as linear and non-linear, in total we do not get 4 kinds of problems. That is, any of the 2 above and any of the 2 below we cannot combine, because in the case of a linear optimization problem you cannot have it unconstrained, because linear functions go on reducing in a certain direction, in certain directions. So, if there is no constraint on the variables in x, then they are unbounded on the lower side as well as on the upper side. So, linear unconstrained optimization problem does not exist. So, if it is a linear programming problem, then constraints will be there in any case. So, you get linear programming problem, which are linear constrained problems, are unconstrained nonlinear problems, and constrained nonlinear problems, which is the most difficult. Now, before going to the methods for multivariate optimization, which is going to be our main focus, let us quickly recapitulate the ideas of single variable optimization, with which you are conversant already to a good extent. Say for a function f of x, a single variable, a point x star is defined as a local minimum point if there is some epsilon such that the value of f x at all other points, that is all points in that neighborhood, in this epsilon neighborhood, that is epsilon on this side and epsilon on that side, in all at all other points the function value is greater than or equal to the function value at the current point x star. Then you will define the point x star as a local minimum point. Now, schematically, let us have a look at this. There is a function which is defined over the interval a to b. In this particular case, x1 is a local minimum point, and then x2 is a local maximum point. x3 is neither a local minimum point nor a local maximum point, because there is some point close to x3 on the right side at which the function value is likely to be lower, and this will not be satisfied. So, this is not a local minimum point. It is neither a local maximum point, because on the left side of it the function value is likely to be higher. Okay. So, this is a point of inflection. Now, here you find it is again a local minimum point. So, see the difference between this point and this point. Here it is a clear local minimum point, here it is not. Here it is, here the function profile comes from upward and then becomes constant for a while and moves up again. So, this is a minimum point. Here the function profile comes downward, becomes constant for quite long and then goes down. But then when we say that it becomes constant for quite long, it is not necessary that over an interval around x3 it is constant. It is just that it touches its tangent more smoothly, that is possibly first order and second order derivative both are 0. Okay. Here you find that a constancy kind of situation lingers for a little more smoother interval around it, and then it goes up. So, it is a minimum point. You will notice that even b is a minimum point. Now, here the curve does not become flat, but since beyond b the function is not defined, so this is also a local minimum point. The function is defined only on the left side, and all points on the left side are above the current point. So, b is also a minimum point. So, in this schematic, x1, x4 and b are 3 minima. On the other hand, a, x2 and x5 are maxima. x6 is neither a minimum nor a maximum. Similarly, x3 is neither a minimum nor a maximum. Now, that is according to this definition, and those points where the function is differentiable, there you can find out certain optimality criteria based on the derivatives, and that is the first order necessary condition says if x star is a local minimum or maximum point, and if the first derivative exists, then it must be 0. If the first derivative is non-zero at that point, then if it is positive, then on the right side it will go up, the function value will go up, on the left side the function value will go down. Similarly, if the derivative is negative, then reverse will happen, one side will be higher, other side will be lower. So, that way it can be, the point can be neither a minimum point nor a maximum point. Therefore, for being local minimum or maximum point, the first derivative can neither be positive nor negative, and therefore it must be 0. Now, note in this case what is happening. The first derivative is 0, the tangent is horizontal. What is the tangent before and what is the tangent after? That is, what is the slope before that point and after that point. Before that point the slope is negative, going downwards. After that point the slope is positive. At that point the slope is 0. So, you find the first derivative is 0, and first derivative as x changes, as x increases, the first derivative is first negative, then 0, then positive. That means the first derivative is an increasing function of x, which means that the second derivative is positive. So, that gives you the second order condition. Second order necessary condition is that the second order derivative is non-negative, positive or 0. That is why this is also a minimum point, this is also a minimum point, okay, but this is not. So, it is necessary, but not sufficient. Second order sufficient condition will be that the second derivative is positive. Now, if the second derivative is 0, then it satisfies the necessary condition, but not the sufficient condition. So, to resolve the situation, you need to go further. The way to go further is through Taylor series. So, if you write the Taylor series of f of x around a given point x star, the candidate point, then you get f of x star plus delta x is equal to f of x star plus first order term plus second order term plus third order term and so on. Now, keeping f x star, that is transposing f x star on the other side, you talk of the change in function value. So, the change in function value from x star to x star plus delta x at that neighboring point. The change in the function value from Taylor series is given like this. Now, here you find that as long as the first derivative at that point is not 0, for small enough interval, for small enough delta x, this first term will dominate this series, and the sign of this first order difference will depend on the sign of delta x. That is, whether you are taking the other point on the positive side or on the negative side, whether delta x is positive or negative. Depending upon that, the first order term will change its sign, and that term is going to dominate the series for sufficiently close points, for sufficiently small delta x. That will mean that on one side this will be positive and the other side it will be negative, and therefore, the difference being positive on one side and negative on one side will preclude the possibility of the current point being a minimum or maximum point. Therefore, for the current point to be a minimum or maximum point, it is necessary that this derivative vanishes, the first order necessary condition as we saw just now. If this point vanishes, then for sufficiently small delta x values, this entire series will be dominated by the second order term, and the sign of the second order term does not depend on the sign of delta x, because delta x is appearing as a square. So, irrespective of whether you go this way or that way, delta x square is positive. It will depend upon the derivative sign. If the derivative is positive, then this will be positive for sufficiently close points. Now, if it is positive, that means the neighboring points both sides have higher function values, right. So, that will qualify the current point as a local minimum point, right. Similarly, for negative values of value of this, it will be a local maximum point, and that is why the second order derivative being positive with the first order derivative 0 is sufficient condition for the current point to be a minimum point. If it is 0, if the second order derivative is also 0, then again the series will be dominated by the third order term, the sign of which will again depend on delta x, because you see delta x cube appears, odd power. So, this goes on. So, therefore, now looking at the pattern, you can say that for an extremum to occur at point x star, the lowest order derivative with non-zero value should be of even order. If up to third order it is 0, fourth order is positive, then again it is a local minimum point. So, that gives you a working rule for determining candidate points and then classifying them as minimum, maximum and so on. So, first of all, you evaluate the first derivative and set that equal to 0, and solving that you try to find out candidate points x star. So, such a candidate point is to begin with a stationary point. It may be a minimum point or a maximum point, or it can be a saddle point, an inflection point. So, after we have captured certain candidates for further test, then at that point, at those points, we evaluate higher order derivatives till one of them is found to be non-zero. If we go on finding derivatives and several of them are found to be 0, second order, third order, fourth order, fifth order, then we stop at that point where first non-zero derivative is encountered. If its order is odd, then the current point x star is an inflection point, coming like this, going like this, or coming up and then going further up like this. If the order of that first non-zero derivative is even, that is either the second or the fourth or the sixth and so on, then that will be a local minimum point or a local maximum point, depending upon whether that derivative is positive or negative. So, this much you have studied long back in 12th standard calculus itself, and this was the working rule for finding maxima and minima at that stage. However, it requires the solution of an equation. Okay. Now, solution of an equation is always not an easy task. In the previous lecture, we also discussed the situation where for solving an equation we formulate it as an optimization problem. Okay. So, equation solving is also not always extremely easy. There may be equations which are very difficult to solve. So, quite often we do not try to rely on the equation solving process to capture the candidate points, but we follow an optimization based algorithm directly to find the minimum point. Now, for that there are several methods. Now, there are some of these methods depend on gradient one way or the other, and some other do not depend. That is, some of them depend on derivatives, some of them do not depend. Even those which depend on derivatives, some of them use derivatives explicitly and others do not. For example, Newton's method, which is reminiscent of the Newton-Raphson method of equation solving. So, in the case of equation solving, we had when we required the solution of an equation like this, then our typical iteration was x k plus 1 is equal to x k minus phi of x k divided by phi prime of x k. Right. Now, here we are talking about minimizing the function f. Now, we know already that at the minimum value, at the minimum point, f prime is going to be 0. So, why not try to solve f prime x equal to 0? So, if we want to solve this equation f prime x equal to 0, then in place of phi, if we put f prime, then we get f prime here, f double prime here, that is second derivative. Okay, that is the typical Newton's method for optimization of a single variable problem. Okay, single variable function. One difficulty of this is that this formulation will not differentiate between a minimum point and a maximum point, or an inflection point with 0 derivatives, 0 first derivative. Now, here itself, in the case of second derivative, if we replace that with a finite difference kind of derivative formula, then we get this formula, which is the second method. Now, in the second method, you will notice that we do not need the second derivative, but we need the first derivative and the function value at 2 points. Okay. So, Newton's method works with a single point up to second derivative, which also means that the second derivative should exist. Second method works with 2 points at a time. That means, in the initial case we need to give it 2 points and only up to first order derivatives. Method of cubic estimation is another method which uses function values and derivative values at 2 points. Starting with 2 points, it evaluates the function value and the derivative value at these points, and then that means that we have got total number of 4 conditions, 4 conditions in total, 2 conditions at this point and 2 conditions at that point, function value, derivative value, function value, derivative value. And with this kind of 4 conditions, we can fit a cubic function in the local neighborhood. Okay. That is, for the local neighborhood, we can approximate the actual function by a function of this kind, a cubic fit. So, as we impose the conditions, that is at x0 and x1, we are prescribing the function value and the derivative value. As we prescribe these conditions on this, we essentially get 4 conditions, 4 equations, 4 linear equations for that matter, in the coefficients a0, a1, a2, a3. From that we can determine these coefficients, and then we say that we look for that point where this cubic function is minimized or its derivative is 0. So, that we get in terms of a1, a2, a3, etc., and that becomes another point. Now, out of the 2 original points and this third point, we retain 2 points and drop one of the old points. Again, at 2 points we evaluate the derivative and some derivatives and function values are already there. At the new point, we evaluate the function and derivative and continue. So, this method is called the method of cubic estimation. Similarly, there is also a method of quadratic estimation that operates not with derivative at all, that operates only with function values, but at 3 points. So, to begin with, you need to prescribe 3 points to this method, and through those 3 points, only with the help of function values, the algorithm frames a quadratic a0 plus a1x plus a2x, oh, this is square, a2x square, only up to this, and by fitting that quadratic with 3 coefficients, because of with the help of 3 function values, and then asking for its gradient to vanish, it gets the new point. So, this method is method of quadratic estimation. So, in which only function values are used, no derivatives. Now, note that whether some of these methods use derivatives, here up to second derivative, here and here up to first derivative, here no derivative, but then still all these 4 methods in an indirect manner refer to the vanishing of derivative, because that is the test, that is the requirement based on which the new point is generated. So, the disadvantage of all these methods is that it treats all stationary points alike and does not differentiate between a minimum and maximum. That is a disadvantage in these methods. So, if the problem is such that it has a minimum and perhaps not a maximum, then any of these methods will work out nicely. On the other hand, for a problem which has lots of minima and maxima, this kind of a method runs the risk of reaching a maximum point. There are some other methods which first insist on a bracket, and second do not make any reference, not even an indirect one, to the derivative. First, what is this bracketing? In the case of equation solving or root finding problem, we referred to the continuity of a function and said that if there are 2 points x0 and x1, and the sign of fx0 and sign of fx1 are different, one is positive, the other is negative. That means, due to continuity, it is necessary that at one point in between x0 and x1, the function is bound to cross the 0 line, and that is the root. So, that was the way to bracket the solution of an equation. In the case of minimization problem, the bracketing has a slightly different meaning. If there are 3 points x1, x2, x3, x1 less than x2, which is less than x3, such that at x2 the function value is lower than both x1 and x3, then we say that between x1 and x3 there is a solution. Okay. So, if we have a pattern of the function which is like this, then we can say that in between this there must be a minimum point, because it is known that from this point the function value has gone down, and then it is known that from this point the function value has gone up. So, in between, what is the point here or somewhere where that actual trend is made. Now, these 3 could be like this, in which case the minimum is here, or it could be like this, in which case the minimum is here. Okay. So, this is important. So, bracketing in the case of minimization problem requires 3 points, and the pattern or trend of downward and then upward should be established to identify a bracket. Now, once such a bracket is there, some of the optimization methods, some of the single variable optimization methods try to continuously squeeze the bracket. Bisection is one possible way. For example, if we know that in between this there is a minimum point, then in a similar manner of bisection we can try to see that whether this half is going to constitute a bracket or this half is going to constitute a bracket. That is, which half of the complete interval is going to retain the nature of a bracket, and then like that we can squeeze and find a solution. However, compared to bisection, 2 other methods are found to be more efficient. that is, they conduct the same job with the same accuracy with less number of function evaluations. One of them is Fibonacci search, in which the interval reduction is not through half at every iteration, but in a variable size, in a variable fraction, the interval is reduced. The squeezing takes place at a variable rate, and the subintervals are decided based on Fibonacci numbers. Okay. So, Fn minus 1 by Fn, in this way you try to reduce the size, and through this measure what you ensure is that for this interval, if you evaluate one point here at evaluate the function at one point here and at another point here at same distance from the two endpoints of the interval, and then either you retain this point and throw away this, or you retain this and throw away this. So, out of these, whichever is larger, that whichever maintains the bracket, that is retained and the other is removed from here. And that way what happens is that in the next, the way the fractions are generated with the help of Fibonacci numbers, it becomes obvious that in the next round, in this interval, the 2 points that will be needed where the function will be evaluated, out of that one will be this itself and the other will be symmetrically placed here. So, at every new iteration, the two new points, the two new internal points, interior points that will be needed, one of them is one of the old points. So, at every in iteration, only one new function evaluation is made, and every function evaluation is used twice on an average. Now, from the Fibonacci search method itself, one particular another search is developed, which is golden section search. In that, the interval reduction fraction is not variable, but it is constant and it is equal to this golden section. So, in the golden section search, a similar operation is done, but at every iteration the interval reduces by this fraction, which is the golden section ratio. Now, through this squeezing of the bracket, through this interval reduction at every step, there will be a stage where the interval is so small, that is smaller than your requirement of accuracy. For example, if you wanted the solution up to an accuracy of 0.01, then by the time the size of the interval itself is less than 0.01, you say that any of these points is good enough as a solution. So, that is the way Fibonacci search and golden section search method operate, and they keep on squeezing the bracket and finally make the bracket so small that any point in that bracket is good enough for the required accuracy. Now, with this much background of single variable optimization recapitulated, now we will go to discuss the actual problem of our focus, which is multivariate optimization. First, unconstrained optimization in this lecture and the next, and then we will study a little constrained optimization. Now, in an unconstrained minimization problem, a point x star is called a local minimum of the function if there exists a delta, whatever small you like to choose. If there exists some delta such that within a ball centered at the current point x star and radius delta, all points have the function value which is greater than or equal to the current point under question, then the current point x star is called a local minimum point. Now, this is the basic definition of a local minimum point, and note that we are talking about local minimum point, and most of the algorithms which we will be discussing cater to the problem of finding a local minimum point only. Now, you can talk of finding all the local minima, several local minima, and then out of them choose the smallest one and hope that that is the global minimum. That is one option if you want, if your problem demands to find the global minimum. Now, if the function is differentiable, then you can work out some optimality criteria, as we did in the case of in the case of single variable problems based on derivatives. Say again, making an approach to the Taylor series, we find that if x is a point neighboring x star, then the difference of function values f x minus f x star will be the first order change, which is gradient transpose delta x, where x minus x star is delta x, plus half delta x transpose Hessian, the second derivative matrix, into delta x, plus the higher order terms. So, up to this is the truncated second order truncated Taylor series. Now, for x star to be a local minimum, again you argue in the same manner that as long as this gradient is non-zero, there will be some directions delta x along which the function will increase, and some directions along which the function will decrease. Now, a direction along which the function increases will ensure that in the opposite direction the function will decrease. So, the current point cannot be minimum or cannot be maximum. So, for minima or maxima for any extrema, the first order term must vanish, which means the gradient as a vector, the complete gradient vector must vanish, all the partial derivatives should vanish, and then this second order term dominates the series for sufficiently small delta x, and in that case the sufficient condition is the positive definiteness of this Hessian matrix at that point, which will ensure that for all delta x it is positive, that is sufficient condition. Necessary will be that it is positive semi definite. An indefinite Hessian matrix with some eigenvalues positive and some eigenvalues negative will characterize what is called a saddle point. Note that we can talk of the first order condition or second order condition only when the function is first order differentiable and second order differentiable and so on. Okay. So, only for first order only for functions which are differentiable up to the first order you can talk of first order condition, and only for functions which are differentiable twice you can talk of the second order condition. Okay. Now, with these optimality criteria we proceed towards a few further issues which will be found quite useful when later we consider multivariate optimization methods. And the most important issue in that direction is convexity. So, there are two aspects of convexity, a convex set or a convex domain and a convex function. Now, in the Rn, that is n dimensional real space, a set S or a region is called a convex set if for all pair of points belonging to that set the complete straight line segment joining them is also inside the in the set. That is, this region is not convex, because in this you can find 2 points which belong to the set, but the straight line segment joining them does not completely lie within the set. Now, on the other hand, this region is convex, because for every 2 points inside the set, the straight line segment joining them will be completely inside the set, inside the region. Now, for unconstrained optimization problem, the region question will not arise, but it will arise in constrained optimization problems, but then it will be important because further we will be defining a convex function which can be sensibly defined only in a convex set or convex domain. Now, saying that the straight line segment joining the 2 points is saying this, that is, for alpha belonging to 0 to 1 interval, alpha x1 plus 1 minus alpha x2, that is, for alpha equal to 0 you get x2, for alpha equal to 1 you get x1, and for any intermediate value you get a point in the line segment joining x1 and x2. So, such a set for which for every 2 points this will hold, that the entire straight line segment joining the 2 points also will belong to the set, will belong to the region. Such a region is called a convex region or a convex domain. Now, over a convex set, over a convex domain, you can define a function f x, which will be a convex function if for every 2 points belonging to that region and alpha again between 0 and 1, the function value at an internal point in that line segment is less than equal to the corresponding linear interpolation between the function values at the end points. Now, if this is not very clear, then think of it in this way, that is, you have the function value at x1, that is f x1, and you have the function value at x2, that is f x2, and you want the function value at a point which is intermediate between x1 and x2, say at 0.2 fraction of the distance from x1 to x2, that is from x1 to x2 in that line segment 0.2 distance from x1 and 0.8 distance from x2. Now, 0.8 into x1 plus 0.2 into x2 is that point. You evaluate the function at that point, and that is the function value here. Now, rather than evaluating the function value at that point, if you had tried to interpolate it from the function values at the 2 end points, then you would get this approximation, right, 0.8 into f x1 plus 0.2 into f x2. Now, the function is called a convex function if in every such situation this interpolated function value is always an overestimate, that is chord approximation, interpolated approximation. If it is always an overestimate compared to the actual function value at all intermediate points, then it is called convex function. Equality is permissible, that is, it can be equal. So, schematically seeing, this is a convex domain because any 2 points that you can take in this will ensure that the straight line join of those 2 points is completely inside. Now, this is an example, this graph of the function that is shown is a convex function, because you see that if you take 2 points x1 and x2 and the function values here, now a linear interpolation between them, a chord approximation, will be given like this. So, at this point the function value through a chord approximation will be found to be this, whereas the actual function value is here, actual function value is lower and the chord approximation is higher. Chord approximation is an overestimate. So, this kind of a function is called a convex function, that is, for being a convex function, such a thing must happen at every intermediate, every pair of points for every intermediate value. Okay. Now, you will see that other than the chord approximation, if you wanted to make a tangent based approximation, that is, you know the function value here and you want to, you know the derivative also at this point, and based on the function value and the derivative through a first order Taylor series, you want to approximate the function value somewhere else, that is the tangent approximation, and the tangent approximation will be always an underestimate, it will be lower. See, the tangent is going lower on this side as well as on that side, compared to the actual curve, actual graph, the tangent approximation is lower on the left side as well as on the right side. So, such is the property of a convex function, and the chord approximation is an overestimate that actually in a way implies that the tangent approximation will be an underestimate, and that you can show through a few small steps, which we will not go into the detail currently. The only thing that we need to stress at this point is that this gives you a first order characterization of convexity. This is the 0th order characterization of convexity, which is the definition in terms of only function values, and this is equivalent to the first order characterization of convexity, which you can talk of if the function is first order differentiable, that is, f x1 is greater than or equal to f x2 plus gradient transpose x1 minus x2. You can work out a second order characterization also through another few small steps, and that is actually quite straightforward. The second order characterization of convexity is that the Hessian matrix, the second order derivative matrix, is positive semi definite. It is, the function is strictly convex if it is positive definite. On the other hand, if it is positive semi definite, then it is just convex. There is a certain class of problems in which the region, the domain, the feasible domain is convex, and the function that we want to minimize is also convex. Such a problem is called a convex programming problem. That is, we try to minimize a convex function over a convex set, and in that kind of a situation, a local minimum is also a global minimum, and all minima are connected together in a convex set. So, convexity is a very strong condition on a function. Further, further nicely behaved function you will find in a quadratic function, which could be convex or could be non-convex also, but a convex quadratic function turns out to be a benchmark problem against which all optimization algorithms are qualified. A quadratic function is like this, and if you try to find out its gradient and its Hessian, then you will find very easily through first order and second order derivatives that the gradient is this Ax plus b, and the Hessian A is constant. Quadratic function, so second order derivative should be constant, and Hessian is this matrix A, the second order derivative. Now, what kind of a matrix is this Hessian A? If it is positive definite, then you will say that it is a convex quadratic function, and quite often when we use a quadratic function as a benchmark problem, then we consider convex quadratic function in which the Hessian A is positive definite. Now, if A is positive definite, then it is non-singular as well, which means that this equal to 0 will have a unique solution, Ax equal to minus b will have a unique solution, and that unique solution will satisfy the first order condition, gradient is 0, and the Hessian is positive definite anyway, that together will satisfy the sufficient condition for that particular point to be a local minimum, and that is the, that since 0 gradient has that as the unique solution, so that unique solution is the only minimum point of the function. If A is positive semi definite, then it is singular as well, and in the case of singularity, this system of equations, this equal to 0, may be consistent or may not be. Okay. So, if it is consistent, that is if minus b is in the range of A, then in the case of singularity of A, positive semi definiteness, you will have infinite solutions, and all those points, all those solutions, all those infinite solutions of this are local minima and global minima as well, and they are together connected, that is they are distributed over an entire line or entire plane like that. So, that is again a convex set. If A is positive semi definite, but it is this system of equations, this equal to 0, is inconsistent, that is if minus b is not in the range of A, that will mean that the convexity is not a problem, but 0 gradient condition is not satisfied anywhere. So, in that case the function is unbounded and the minimization problem has no solution. These second and third cases, the first case is very simple. The first case is like this. Okay, this is the shape of the function. Okay, so this is a minimum point. 0 gradient, 0 derivative condition is satisfied only here, and the function is convex everywhere. Okay, so second derivative matrix is positive definite everywhere, it is constant. So, this is the unique minimum. On the other hand, the second case here, A is positive definite, positive semi definite, that is singular, and minus b is in the range of A. That means that there are points where the gradient vanishes. That is the function profile, which is like this cylinder. In this cylinder, you find that it is convex, okay, semi definite, because you see along this direction it is straight, and along this direction it is convex, okay, like this. So, this is a semi definite case, and when you try to solve Ax plus b equal to 0, 0 gradient, 0 slope, then all these points satisfy the 0 gradient condition, and therefore, this entire line is the solution of the minimization problem. All these are the points at which the level of this function is lowest. Okay. On the other hand, the third case here, this one is the same cylinder, but not placed horizontally, but like this. In this case again, it is semi definite, okay, because there are directions in which there is no convexity concavity, and there are directions in which there is convexity. So, here 0 gradient condition, this Ax plus b equal to 0, that condition is not met. That is, there is no point which satisfies the 0 gradient condition. As you can see, on this surface there is no point at which the gradient is 0. So, that is why the function is unbounded. That is, along this direction you can go on going downward, and there is no end to it, okay, compared to this case where you cannot go downward. Okay. So, 0 gradient condition is not met in this kind of a situation at any point. So, that is why in this case there is no solution. Now, as benchmark problem, we typically consider those quadratic functions for which the Hessian is positive definite, non singular case. Now, for an optimization algorithm, we need to have a good picture, a clear picture of how a typical optimization algorithm operates. Typical way to operate for an optimization algorithm is to start from a current point, move to another point which is hopefully better than the first. Now, there are three questions that arise in this process. First is which way to go, second is how far to go, and which decision is taken first. If we first decide the direction, which way to go, and then decide how far to go in that direction, this gives us one strategy of optimization algorithm, that is called the line search strategy. On the other hand, if we first decide that within this much distance we are ready to go, and then we decide that within this much distance in all directions which direction to take and how far to go, that is how far we are ready to go, if we take that decision first and this decision we take later, then that is a strategy which is called the trust region strategy. Now, there are some algorithms which can be implemented in both the strategies, some of them can be implemented in only one of the strategies. For any optimization algorithm, there are two questions that arise. One is the question of global convergence, that is whether at every step the algorithm makes an improvement in the function value, whether it approaches the optimum point, and that is the issue of global convergence. It is in terms of guarantee, whether there is a guaranteed decrease of the function value, whether there is a guaranteed approach towards the minimum point. The other issue that arises in terms of convergence of algorithms is the local convergence, that is what is the speed of approach if we start sufficiently close. So, global convergence refers to the guarantee of approach from anywhere in the solution space. Local convergence refers to the speed of approach if started sufficiently close. So, some of the methods have linear convergence rate, which are typically the slower methods. Some have quadratic convergence rate, which are typically fast methods, and there are algorithms which are in between. Now, with this much background, in the next lecture we will try to study optimization methods, and currently the points to note are here, and quite a few exercises are there in this lesson, in this chapter of the book, and some of them you must attempt on your own to be very conversant with the idea behind this subject matter. Next lecture we continue into optimization methods. Thank you.